This is a video about conservation of momentum in 2 dimensions. Let's check out this simulation in which there's not a collision between these 2 objects. There's this 1.5 kilogram object that's going to go downward, and this 0.5 kilogram object that's going to go to the right. We'll find that they won't collide, and we'll look at the momenta before and after the collisions. So at the beginning of that simulation, if we look at the smaller object first, in the horizontal direction, we would take its horizontal velocity and multiply it times its mass to get 0.50 kilogram meters per second in the horizontal. And because it's not moving at all in the vertical, it's got no momentum in the vertical. If we look at the larger mass and its horizontal direction, we find that multiplying its mass, 1.5 times its horizontal velocity, gives us 0 because it's not moving in the horizontal. However, if we take its vertical velocity and multiply it times its mass, we get negative 0.50 kilogram meters per second. If we add up the horizontal momentum and the vertical momentums, here's what we get. We get 0.500 kilogram meters per second of both objects at the beginning of the simulation, and at the end we get negative 0.50. Now in this particular simulation they don't collide, so at the end we would still expect to have the same momentum and the same velocities. So if we look in the horizontal for the smaller object, we still get 0.500 and 0.00, and for the larger object in the horizontal we still get 0.000 and negative 0.750. And because nothing's changed, when we add these up we still have the same results. So if we ask ourselves, is the momentum conserved, we would definitely say yes, because the horizontal momentum before is equal to the horizontal momentum at the end, along with the vertical momentum at the beginning and the vertical momentum at the end. Now, I want you to check out this next simulation and please fill out the data tables yourselves. Alright, so you watch that simulation, and what I want you to do now is to add up your horizontal and your vertical components before the collision and your horizontal and vertical components after the collision, and determine if indeed the momentum is conserved. Now let's check out the momentum method in 2 dimensions. You'll notice that the only thing that's different is what we've added to step 5. The fact that we need to state that the horizontal momentum is conserved and the vertical momentum is conserved. So let's apply that in an example. In this example, we have a 0.150 kilogram object at 50 degrees relative to the vertical, moving 0.900 meters per second, colliding with this other blue object that's moving horizontally only at 0.540 meters per second, and its mass is 0.20 kilograms. They collide right there, and the blue object bounces in this direction at 35 degrees with the velocity of 0.700 meters per second. We want to find the velocity, the final velocity of the red object and the angle relative to the horizontal. So we follow all our steps. First step is to draw a labeled picture, and the picture is already given for us. The before and after motion map, so motion maps would look like that. So that would be for that object. And for this object, it's a little redundant here since they show the directions, but since it's part of our method, we'll include it. Then it says write a momentum conservation statement like momentum is conserved. So I'll just circle that there. And then we'll include if true inelastic or elastic. They're not sticking together and it doesn't tell us it's a completely elastic collision, so we'll skip step 4. And then we need to write our general equation. And in this case, because it's in 2 dimensions, we want to write the equation in the horizontal and the equation in the vertical. So next we want to substitute our correct values. So there's our equation in the horizontal. So let's look at momentum as it's conserved in the horizontal direction. And the way we do that is by looking at each individual momentum or momenta. So these are the momentas in the horizontal for each object before the collision, and these are the momenta for each object after the collision. Now, each object is made out of a mass and its individual component of the velocity. So notice that these masses don't change before and after, but the components of the velocities do. So this is m1 v initial in the x direction. This is v2 initially in the x direction, and this is v1 in the after the collision, the velocity, and this is the velocity of the number 2 object after the collision. So then we just go in and plug in our values. The masses are pretty straightforward. Those just get plugged into the equation as we would expect. So we have to figure out what each of these components is. So this value right here is the horizontal component, which would be right there. It's the sine component of the red vector. So this represents this vector right there in the horizontal. My other object has no vertical component to it. It's all horizontal. So notice that its velocity doesn't include a component. We just plug in the 0.54 meters per second. Then after the collision, since we're looking for this component here to help us find VF1, that's our unknown. V1, the horizontal component of the velocity after the collision. And for the blue object, there's a mass, and we're looking for this value, which corresponds to this component of the blue object after the collision. So you notice that's the cosine component to it. So those are all the horizontal values. So we need to solve for V1F, and I'll let you do the math. Pause the video if you need to. And we find that V1 final turns out to be 0.63 meters per second. Now let's look at how we would do this in the vertical direction. So once again, we have to state the momentum equation in the vertical. Then plug in each individual momenta for each object. So this is telling us that the momentum should be the same. The total momentum should be the same before and after. And this is telling us that the momentum in the vertical before the collision should equal the momentum in the vertical after the collision. Then we plug in each individual value in the vertical. And for this component in the vertical, we find that that is the cosine component, and we're going to use a negative sign because it's going downward. This has no vertical component, so that drops out. For V1 final, we're looking for that component. That's our unknown. And this is the component for the vertical after the collision of object 2. Notice that that's the sign component. Once again, it's important to look at the negative signs. It's pointing downward, so that's why we've got a negative sign there. We have to solve this for V1 in the final, and we find that this is the equation. Or I'm sorry, this is the answer. In our last step, where we solve and include the units, we found that the horizontal component, which was this component right there, was 0.63 meters per second, and this component is 0.12 meters per second. So solving that using Pythagorean theorem gives us a value of 0.64 meters per second as that value there. It's the hypotenuse of that triangle, and the angle, this angle here, is 11 degrees if we use the inverse tangent. All right, now there's a special condition that we need to be familiar with. Physics B students just need to be able to set this up, but Physics C students need to be able to actually derive it. So Physics C students, you need to derive this, derive these equations from these starting conditions, Physics B students, all you need to do is set these up and memorize these equations. All right? So here's this one-dimensional special condition. When we've got a frictionless surface and an object, let's call it object A, it's moving with a velocity, and it collides with object B that is not moving, and the collision is a completely elastic collision, that means we need to use both the conservation of kinetic energy and the conservation of momentum. Remember, we always use conservation of momentum in every single type of collision, but specifically in an elastic collision, we will also include the fact that the kinetic energy must be conserved. So once again, B needs to set this up and memorize these equations. C has to be able to go from this setup to solving it. So there's a little bit of help as far as seeing what you will need to do to get from those equations down to these equations down here. All right, so feel free to pause the equation, Physics C students, so that you can write down what equations you need, and you need to be able to derive these equations there. These are examples of things we will end up doing in class.